Assalamualaikum Pak Anton.
Waalaikumsalam, Bu Aida ya.
Iya, saya Aida Pak.
Salam kenal.
Sambil menunggu ya Pak. Salam kenal nih Bapak.
Ya.
Assalamualaikum Pak Anton.
Waalaikumsalam. Datang
Assalamualaikum
Bu
Pak
Aida.
Anton.
Bu Aida.
Iya,
Luar
saya
bila.
Aida Pak.
Berarti.
Sambil menunggu ya Pak.
Waalaikumsalam. Terima
Salam
kasih
kenal nih
sudah
Bapak.
menyempatkan waktunya untuk mau jadi guest
Assalamualaikum Pak
lecture di
Anton.
Universitas Ibnu Khaldun, khususnya Fakultas Teknik. Waalaikumsalam.
Assalamualaikum Pak Anton. Iya, saya Aida Pak.
Halo,
Sambil menunggu
tes.
ya Pak.
Waalaikumsalam.
Ya.
Terima
Salam
kasih
kenal nih
sudah
Bapak.
Selamat siang,
menyempatkan
Pak Anton.
waktunya
Terima
untuk
kasih atas undangan yang
jadi
telah
guest.
diberikan. Terima kasih juga atas kesempatannya. Semoga lecture hari ini bisa bermanfaat buat adik-adik mahasiswa di Universitas Ibnu Khaldun dan juga untuk publik di Indonesia pada khususnya.
Iya.
Saya juga minta maaf ini Pak, suara masih belum normal kembali seperti semula. Jadi mohon maaf Pak Anton jika nanti ada batuk, kedengaran suara batuk.
Naik kuansi. Nggak masalah. Nggak masalah. Terima kasih. Jadi nanti rundown-nya nanti ada ngaji dulu, pembukaan ngaji, terus 10 menit sambutan dari Pak Dekan, baru nanti dari saya 5 menit perkenalan, baru lecture kayak gitu. Mau dua lingual atau satu bahasa boleh sih. Karena ini judulnya internasional, boleh pakai bahasa Inggris, tapi sebetulnya pengennya ada rasa lokalnya juga, jadi nggak masalah untuk dua bahasa.
Ya. Baik Pak, saya usahakan nanti dicampur dengan bahasa Indonesia untuk penjelasannya gitu. Tapi saya mohon maaf nanti kalau ada bahasa Inggris kadang-kadang kebawa Pak Anton.
Iya. Jadi 90% bahasa Inggris nggak masalah.
Nggak masalah. Ya.
Terutama untuk istilah-istilah mungkin bisa dijelaskan bahasa Indonesianya gitu biar paham. Gitu paling. Kita tunggu dulu.
Halo, Eja.
Selamat datang Pak Kindi, Bu Tika, siapa lagi?
Assalamualaikum Pak Anton, apa kabar?
Waalaikumsalam. Waalaikumsalam. Alhamdulillah baik.
Oke, alhamdulillah. Oke, terima kasih Pak Anton hadirnya ya.
Ya, terima kasih sudah menyempatkan hadir dan mensukseskan acara ini. Oke. Sudah jam 1 WIB ini, ada jam 2 pas tepat. Kita buka saja ya. Kita buka.
Baik.
Ya, bismillahirrahmanirrahim. Kan untuk adminnya, siapa adminnya? Pak Asep ya, bisa direkam. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Rabbi zidni 'ilman warzuqni fahman. Pertama-tama kita panjatkan puji dan syukur kehadirat Allah Subhanahu wa taala yang telah memberikan kita kesempatan untuk bisa mengadakan acara kuliah internasional online class for the first session dengan tema carbon dioxide capture and storage yang akan dibawakan oleh pemateri kita Dr. Ardila Hayu Tiwi Karama. Dan tak lupa kita panjatkan salawat kepada junjungan kita Nabi besar Muhammad Sallallahu Alaihi Wasallam. Semoga salawat dan salam tercurah kepada beliau dan juga kepada para sahabat dan para pengikutnya hingga akhir zaman. Kita mulai acara kita dengan pertama, yaitu pembacaan ayat suci Al-Quran yang akan disampaikan oleh Pak mahasiswa Pak Setiawan Kahim, sudah datang? Setiawan mana? Kalau belum hadir, kita lanjutkan langsung kepada sambutan dari Pak Dekan, Pak Dr. Nanang. Silakan Pak memberikan sepatah dua patah kata.
Ya, thank you Mr. Anton. Assalamualaikum warahmatullahi wabarakatuh.
Lo udah masuk.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you. Good afternoon, ladies and gentlemen. My name is Muhammad Nanang Ferdianto. First of all, on behalf of Faculty of General Engineering and Science, University of Ibnu Khaldun, Bogor, Indonesia, I would like to welcome all of you to our first international class. Thank you for being here with us today. I also would like to express my sincere appreciation organized this event. Dr. Setia Permana and the team thank you so much for leading our team to create this gathering. We would not have been gathering here without you and your team's effort. Today's seminar is very interesting. We would like to learn about carbon dioxide capture and storage. And Dr. Ardila Hayu Tiwikrama will share the knowledge for us. As we know, carbon dioxide is chemical substances which are colorless gas, having a faint sharp odor and a sour taste. It is one of the most important gases linked to global warming, formed in combustion of carbon-containing materials and fermentation in a cell respiration in organism. The business word carbon dioxide capture and storage is a way of reducing carbon emissions, which could be one of the keys in helping to tackle global warming issues and for environmental protection and conservation. I hope that this seminar will help us build our awareness and knowledge. I think it's an important seminar. That is all for me. Now I will leave the rest to Dr. Anton Royanto Ahmad, our colleague here in Bogor. Thank you to start our class. Thank you very much for listening, Dr. Anton. The floor is yours. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much for Dr. Nanang to give sambutan. Okay, so the class will be international, but I'm requesting Dr. Ardila to give both in Bahasa and English. Like 90% of them will be English, and then 10% maybe in Bahasa, since Dr. Ardila is from Indonesia also. So, but before we begin our lecture, I will try to introduce who is our speaker here. So I will show you her CV. Share. CV. Can you see this? Okay. So yeah. So Dr. Ardila Hayu Tiwikrama now is an assistant professor or in chemical engineering and biotechnology in National Taipei University of Technology. So the educations, she's got her PhD on National Taiwan University of Science and Technology at 2017, and with the supervisor is Professor Lee, and then also got the MT, Master Technique and Sarjana Teknik at ITS, Institut Teknologi 10 November, Surabaya in Indonesia, with the supervisor is Professor Gede. Okay, so today, the current job was an assistant professor, and previously she was a project assistant at NTST, also from 2018 until 2021 for 3 years, and then before that she was a postdoctoral research fellow at NTST, and then she's got several industrial project career board, and the research area is thermophysical properties, phase equilibria technology, carbon dioxide capture and sequestration, and then supercritical carbon dioxide optimization and parameter estimation and gas hydrates. So I think that's all that I want to share about her CV. So this is a very, very interesting topic that we will hear about, the carbon dioxide storage and capture. Okay, I think that's all for me. I will give Dr. Ardila to give her lecture. So
Yeah.
you can start. Thank you.
Thank you very much, Dr. Anton, for nice briefing and also nice preface introduction about me. And also, I would like to thankful about to the Vice Dean of University from the Ibnu Khaldun University Ibnu Khaldun, Dr. Prayudianto Muhammad. Thank you very much for this kindly opportunity and giving me kinds of the chance to share that some experience, especially in the carbon dioxide capture and the storage. So I hope that the professor and also the students here, we can share and learn together, because actually, like, I'm not that expert on the carbon dioxide capture, but I did some experiments about the carbon dioxide capture and the sequestrations. Yeah, probably we can have a chance to build our carbon dioxide capture and storage, especially in our country, in Indonesia. So I would like to ask permission, Dr. Anton, to share my screen.
Yeah, sure. Hostnya.
Yeah.
Okay, but
So it's
by the
fine.
way, if someone want to ask, please
Yeah.
raise. There is 20 minutes question and answer in the end of lecture, but you can post your question at the chat, or you can raise hand. Raise hand. Okay, thank you.
Okay, thank you
Please.
very much. Yeah, thank you so much, Dr. Anton. Yeah, I would like to start with our lecture today is about carbon dioxide capture and storage. In the experiment we did in the Taiwan, and also we tried to develop some carbon dioxide capture also previously when I was studied bachelor and master when in ITS. So today I would like to share our outline includes the introduction of the CO2 capture technologies, because we have a lot of kinds of the technologies here, and I would like to specify in the CO2 capture technologies today, just discuss about the post-combustion captures. Also, we have the apparatus design, CO2 storage, and also utilization. So, like previously, Dr. Anton mentioned about sequestration. Sequestration actually it's similar like storage. Bagaimana kita menyimpan CO2 dalam jangka waktu yang lama. Jadi CO2 storage. Sedangkan CO2 utilization, bagaimana cara penggunaan CO2 untuk transformasi atau untuk konversi ke bahan-bahan kimia lain. So currently that this is very famous because after capturing, like, what's we going to do about the CO2? So what's the application that we could learn? And the five, I would like to discuss or share also about data validation, because we cannot only do the experiment, but also we need to calculate how to validate. Is it our data approach to the theoretical parts, or also just the theoretical parts cannot totally predict the experimental data. So here I would like to share some software that we could use and also some calculations, and the rest is conclusions. So currently, like, I wish that all of the students and also we know about the global CO2 emissions. Currently, it's increasing. Like, we can see that here from 1990 up to 2022. So I'm trying to find 2023, but it's not provided yet about the CO2 amount in the level of in the atmosphere. So probably the projection is about 37.5 gigaton. So it's quite bunch of a lot of CO2 in the atmosphere. That's why currently that we feel our let's say weather is changed gradually, and also it's not stable. Sometimes we feel hot, sometimes also we feel cold, because of the one of the factor is because global CO2 emissions. So if we saw that from this curve that CO2 emission sources is increasing, except in the pandemic, because not many people go out by the car, by the transportations, and also the activity from industry. As we saw from the figure here, we have the fossil fuel power plants, iron and steel mills, refineries, and also petrochemical industries, cement industries. This is one of the example industry that they give some also promote the CO2 amount, especially the global CO2 emissions. But compare than this industry, actually, like we found that some in the researcher, we found that in the research area that actually the transportation, public transportation also play important to increase the CO2 level in the atmosphere. So what's we going to do, and then how we try to face these kinds of the global CO2 emission, how we can do as we researcher or we in industry, what they can do to reduce the CO2 emission, because we don't want to have the global warming and then the fluctuation, the weather always keeps changing and its effect in our environment. So we have the three known very well fundamental parts about the CO2 capture technologies. First of all, it's pre-combustion. So pre, it means sebelum pembakaran, and post-combustion, setelah pembakaran, and oxy-fuel. So these three, it's kinds of the well-known CO2 capture technologies. So I will provide the meaning of each of this technology. First of all is to capture CO2 in the synthesis gas. So synthesis gas after the conversion of carbon monoxide into CO2. So actually the concentration of the CO2 in the pre-combustion, it's quite large amount. So to remove the CO2 in the efficient way, if our CO2, for example, in industry, they have concentration of CO2 larger than 20%. So this method, it's more efficient compared than the other method. So actually the CO2 capture technologies is depend on the CO2 concentration level in the air, whether in the let's say in the gas mixtures. So we can select according to the concentration. Mostly in the synthesized gas, like the level of CO2 is above than 20%. And the other is post-combustion. This is like the most we would like to focus on to capture carbon dioxide in the exhaust gases. So this is mostly in the coal industry, or probably we in the like electrical or in the industry that they produce the energy, that they have the CO2 concentration, it's a little bit lower than the pre-combustion level. So it's around like 5 up to 15% around. So we can use this technology to remove the CO2. So this actually we try to capture after the gas has been fully burned with the air. Jadi kalau misalnya kita melewati kilang Pertamina, misalkan di situ ada tangki, ada seperti tower yang khusus untuk fuel air burner. Kadang-kadang kalau kita lihat asapnya itu bisa berwarna sampai hitam gitu. Nah itu ada kemungkinan exhaust gasnya itu membuang CO dan CO2 ataupun gas-gas buangan lainnya. Nah di situ CO2 sendiri sebelum kita setelah pembakaran akan lebih baiknya kita melakukan post combustion atau capture ataupun kita bersihkan atau remove CO2 ataupun kandungan CO atau acid gas lainnya sebelum kita rilis air tersebut ke atmosfer, sehingga itu juga akan mengurangi level CO2 di atmosfer. Nah, selanjutnya adalah oxy-fuel. Oxy-fuel ini adalah consisting of the combustion in oxygen with recycling of the exhaust gases, therefore composed mainly of CO2 and water, and purification of the CO2 flow. This is actually seldom the industry use. Somehow, if they have the consist of the wet gases, so they can apply for the oxy-fuel. So practically, the industry prefer to use the first one or the second one. So the mostly capturing CO2, in the industry, they apply the second one because the level of CO2 is not that much, like 5 up to 15%. So this method, it's more practically efficient compared than pre-combustions. So the next, which kind of the chemical solvents and also physical solvent that we use for the CO2 capture. So each of the technique, they have different way. So if we discuss about chemical solvents, maybe any one of you, I would like to ask to the students here, probably like, what's the difference between chemical solvent and the physical solvent? Anyone could give me some idea? Solvent, it's larutan kimia. dan larutan yang ibaratnya solvent. Solvent itu larutan yang prinsipnya dia absorb secara kimia. Sedangkan kalau physical solvent itu secara fisik. Nah, mungkin adik-adik mahasiswa ada yang bisa memberikan ide apa perbedaan specifically antara chemical solvent dan physical solvent. Atau apakah sudah pernah mendengar sebelumnya untuk dua istilah ini? Okay, so it's okay.
Belum
I
sebenarnya.
could share. I could share a little bit. So for the chemical solvents, mungkin adik-adik pernah dengar amines, atau amin solvent, atau mungkin monoethanol amin ya, jenis amin, advanced amin, ammonia. For the capturing, it's quite good. But the process for the regeneration, it's quite complex because the process of the CO2 capture, they have chemical interaction process inside. So to release the CO2 from the chemical solvent, it takes more high energy. Some industry, of course, they practically like to use the amines, yeah, but still the cost, it's quite costly. I mean, it's quite expensive because it's chemical interaction. It's hard to separate between CO2 and the solvent. So solvent, it means the liquid that we use to capture the CO2. Jadi larutan yang akan digunakan untuk menangkap CO2. Sedangkan physical solvent, prinsipnya interaksi or interaction without any chemical reaction inside the solvent. So how we remove the CO2 use the physical solvent? We just play with the pressure. For example, once we increase the pressure, they could absorb the CO2. If we would like to regenerate, we just decrease the pressure and the CO2 will release, and we can reuse again this liquid into the another cycle. So this is physical solvent. So it's more cheaper, and industry practically prefer to use this, but somehow have the weakness. The weakness it was the CO2 capability is not that high compared than chemical solvent. So sometimes it's depend on the design of solvents. So we have another is chemical sorbents. This is typically used by the adsorption. So I wish that the students know that what's the difference between absorption and adsorption. So absorb, it means you will use amount of bunch of the liquid phase to capture the gas phase, right? So we use kita menggunakan larutan dalam jumlah yang banyak untuk menangkap gas. Jadi absorb, liquid ke gas, liquid menangkap gas. Sedangkan adsorb artinya kita menggunakan solid. Di permukaan di solid tersebut dia akan mengadsorb atau akan menangkap CO2. Jadi kerja prinsipalnya itu hanya di permukaan. Jadi adsorption, adsorption, sedangkan absorption itu ke dalam bulk of the liquid. Jadi gas liquid phase itu absorption, sedangkan solid vapor phase itu adsorption. Sekarang ada beberapa teknologi. There is technology that they try to develop like amine enriched sorbents and also metal organic frameworks. This is the famous one. Metal organic frameworks, I will discuss further for this later. And also we have nitrogen CO2 membranes. This is quite interesting, but it's very expensive, especially industry try to double thinking to use the membrane because you need to change the membrane. Membran itu seperti jelly. Kalau adik-adik pernah lihat jelly agar-agar, tapi dia tipis sekali. Jadi jelly-nya itu kita potong tipis, sangat tipis sekali. Jadi seperti layer. Nah, tumpukan membran itu per layernya itu bisa ribuan, bisa ratusan. Sehingga ketika itu ada endapan misalkan di dalam situ ataupun ada kotoran, ketika membran itu harus dicuci. Nah, untuk pencucian membran itu kadang-kadang memerlukan cost. Jadi costnya itu harganya tinggi sekali. Nah, di situ kenapa industri itu nggak terlalu prefer dan it's hard to maintain. Nah, pre-combustion juga ada yang menggunakan chemical solvent, physical solvent, novel ini seperti hydrates ya. Hydrates looks like ice. So like the ice, it's like ice. Inside the ice, they have the gas. So later I will show some picture. We did the hydrates to storage the CO2 and CH4. So CH4 with the CO2 storage and CH4 replacement. Jadi ini teknologi yang sekarang sedang dikembangkan oleh Pertamina untuk mengambil gas metan di tengah laut. Jadi sekarang ini banyak peneliti yang berusaha untuk mencari replacement dari fossil oil. Salah satunya adalah replacement CH4 atau gas metan yang di tengah laut dengan CO2. Jadi CO2-nya akan diinjek ke dalam well sehingga CH4 yang di tengah laut itu atau di dalam laut itu akan keluar. Nah, tentu kan ketika kita ambil sesuatu dari dalam bumi, ada sesuatu yang harus kita injekkan kembali. Nah, di situ kita menggunakan teknologi yang namanya hydrates. That's why the pre-combustion we use, because the CO2 in the large amount. We cannot inject in the well just 5 or 15% mixtures inside the well. And the physical sorbents, the same, metal organic frameworks, physicals also. And oxyfuel, normally they use chemical looping or oxygen transport membrane because this is wet. The gas is not dry. And the post-combustion, pre-combustion, practically the water content is not that much. That's why they prefer to use post and the pre. So first of all, I would like to discuss in here, according to this slide, I give the green box here that I hope that I could share today, and also some hydrates knowledge, how to capture the CO2 inside the mixtures. So we use the first is ionic liquids. So what's the ionic liquid first? The ionic liquids are classified as the type of ionic liquid. Generally, we use 2 or 3 substances. For example, 2 in here is cation and anion. So we use acid-based titration. So mostly to produce the ionic liquids. Jadi kalau adik-adik tanya, apakah ionic liquid itu available dijual? Iya, tetapi harganya mahal. Jadi lebih baik kita sintesis sendiri. So when you synthesize by yourself, you can design the ionic liquids according to their task, according their function. So it's more cheaper to do the experiments, and it's not difficult. Actually, it's not hard to synthesize. So it's just basically cation and anion. So positive, negative, acid and base, acid and base. Jadi acid base titration itu basic dari ionic liquid. Nah biasanya temperaturnya itu we would like to control around 70 or 80, is depend on the ionic liquid mixture. So what's the function of ionic liquids? There are many applications here like nanocarriers, protein stabilization, antimicrobial, biosensing, so solubilization of the drugs. This is mostly in the biochemistry or biochemical. Also for capturing gas. This is ionic liquid also used for the industrial application. So not only CO2 capture, but also here biochemistry is a lot. And also we can use the molecular dynamic simulation or COSMO. Later I would like to discuss briefly about this software, like how we predict the interaction or energy needs, the interaction between the cation anion and then also with the CO2. So here some trends of ionic liquid, like in the market or in the publication, like as we see here, like every year the publication is increased because researchers try to find like why they use the ionic liquids actually, because industry mostly use the organic solvent is not green. It means the vapor pressure is quite high, so it's not good for the process in the industrial process. It's not good for the environment. It's good maybe for the industrial, but it's not good for environment because it's high vapor pressure, easy to release to the environment, and probably is toxic. So we don't want to use this kind of solvent. That's why currently the researcher try to find the best replacements of the organic solvent, use the ionic liquids, deep authentic solvent, or any green solvents. Jadi kalau kita lihat di tren ini semakin meningkat karena researcher ingin mencoba menemukan ionic liquid yang efisien. Dan ionic liquids, this is green solvent, is very low vapor pressures. So currently, like ionic liquid market share also increasing. So like from the Middle East, every country, they try to sell the ionic liquids. You can find in the Sigma Aldrich, somehow they produce these chemicals. So what's the application next? What we're going to do with the trends of ionic liquids? So first, before we do the experiment, actually we did the prediction. So we use here is Cosmo. So later I will give briefly a description about Cosmo. Cosmo, it's kind of the modeling that we use to predict the interaction or the profile surface interaction between the CO2 or acid gas with the ionic liquids. So why we need to predict first? Because we would like to check that this ionic liquid has possible high interaction or not with our compound. So we don't trial and error, but we try to predict first according to the molecular structure. Like here, the ionic liquids, you have the complex molecular structure here, and then you can see that negative surface, positive surface in here, how their interaction. Is it they have positive surface together or negative surface together? So it means that we would like to check the possibility interaction between CO2 and the sulfuric gas with our ionic liquids. Then after we get the prediction, we could synthesize our ionic liquids and try to check the CO2 capture or CO2 solubility in the ionic liquid. So here, if you can see that we have around 5,980 ionic liquids. So it's not one ionic liquids, it's 1,000. And we try to check the melting point, viscosity, solubility, absorption, selectivity, working capacity. Also, we have sensible heat, dissolution enthalpy, excess enthalpy. And how about the stability? Is it stable or it's unstable, toxic, the price also? And we can use as the candidate, the best candidate to absorb the acid gas, also to absorb the CO2 gas. So later, you will obtain the clean syngas. So what's the function syngas? Many we can use the syngas to produce the chemical, to produce the any kinds of the renewable energy for the application. So the CO2 later we can recover. So recover for what? Later we have CO2 storage and utilization. So later I'm going to talk about this. So the Cosmo itself is known as the conductor-like screening model for the real solvents. So this is kind of the quantum chemistry. So basically, they will predict the chemical potential. It's a bit thermodynamics. Actually, they will screening the charge density of the surface. So if you can see in here, this is kind of the one chemical that we predict. This is, you can see positive charge, negative charge. So we can see the possible interaction between this molecule with the CO2. So if the interaction it's quite high in the positive, in the non-polar region, or in the negative charge, probably they have high chance that they can absorb the CO2 very well. So in here we can check the interaction between solute and solvent in the mixture. So then we can also predict the activity coefficient, solubility, partition coefficients, vapor pressure, and the free energy. So this is kinds of another measurement that we can do, not only to check the CO2 capability, but also we can measure like how green our solvent. We always say green, but we never know the vapor pressure. And if you check in the literature data, it's not much actually, like seldom company will share about the vapor pressure. Ya, jadi jarang company ngasih data, apalagi itu specifically-nya itu untuk data perusahaan, mereka nggak akan publish. Jadi untuk konsumsi sendiri biasanya akan ngukur vapor pressure ini jarang sekali data eksperimen yang dipublish untuk mengetahui bahwa ionic liquid atau any green solvent itu benar-benar green. Tetap meskipun green, tetap ada low vapor pressure-nya, tapi itu sangat-sangat kecil sekali. Nah, ini cara sintesis ionic liquids. Jadi ini saya pakai there are two different kinds of ionic liquids. First, this is base, diisopropyl ethylamine, and the acid we have the propionic acid and butanoic acid. So how to do? By the acid-base titration. Jadi di dalam sini kita bisa input basanya diburet, kita bisa inject acid. Nah, ini tuh dibuka di buretnya ini ditetesin slowly, tapi ini sambil dihidupin stirrernya ya. Nggak usah pakai heat. Jadi untuk acid base titration ini biasanya kita lakukan pada room temperature. Room temperature di acid base the stirrernya sekitar 200 about 200 up to 300 rpm. Then slowly until the acid totally comes to the base. So after this we leave for the overnight. Jadi kita diamkan tetap dalam kondisi stirrer selama 1 malam atau 1 hari. Kemudian then we can use the evaporator, vacuum evaporator to remove the extra excess base or excess acid. So we would like to remove some excess. Of course, they will have excess. They are not totally like become all ionic liquids. They have excess. They have also water content. Definitely in the ionic liquids, they will have some water content. So how to remove? We can use the rotary vacuum dryer. So we can use to heat around 40 degrees C and the vacuum pressure 10-2 up to 10-3 until you get the pure ionic liquids. So how to check the pure ionic liquids? We could check by NMR to detect that this is pure ionic liquids, is not acid only or the base only. And the second, we got to know the water content is by Calvisser. Because if you have more water content in the ionic liquids, it will reduce the capability of the ionic liquids to capture the CO2. So it's not that good. Jadi kandungan air di dalam ionic liquids itu sangat berpengaruh terhadap daya serapnya atau daya kemampuan dari ionic liquids ini untuk capture CO2. Semakin sedikit semakin bagus water contentnya. Ini aparatus desainnya itu ada beberapa. Ada vapor liquid equilibrium ini yang kami gunakan, static type, semi flow type, ada juga flow type. Nah, ini jenis-jenis aparatus atau alat ya untuk mengukur fase untuk menentukan kondisi yang optimum. Ini salah satu contohnya adalah phase equilibria analyzer atau PEA. So this is consists of the high pressure cell. So this cell we can use up to 500 bar, and also the temperature is around 473.2 K. So we can see that what happened the phenomena inside. So in here, for example, we use CO2 with kind of some specific solvent. So if we see here that we see this region. So maybe some of you ever saw that the thermodynamics curve. So they have the bubble point, dew point, and then critical point. So this phenomena transition, like each of this point, we can see that the phase transition inside. So since that our application is CO2 capture, so we just operate below or under the critical region. So around here. So it means that this point, it means it contains of around 0.115 or 16, yeah, 16 mole fraction of the CO2. We only obtain the pressure is around 3.8. Jadi untuk satu poin ini tuh menyatakan kalau ini tuh CO2 solubility atau carbon dioxide solubility di dalam solventnya tersebut. Nah, ini cara-caranya. Pertama, alat-alat ini there is consist of the LCD monitor and also magnetic stirrer inside. So magnetic stirrer, the function is to promote the well mixing between CO2 and then also the solvent. So we will use the syringe pump. So this syringe pump is high pressure. So we can use the inside the volume up to 35 until 46 centimeter cubic, the pressure up to 500 bar or 50 megapascal, and the temperature is 473.15 K. So we can, this is have some camera connect to the LCD monitor to check the phase transition. So actually this high pressure, it's occupied by the sapphire window. So we cannot use the glass because it's high pressure. So we need to use the specific material. It's a sapphire window, and also they have the light source in here to see the what happened, like which kind of the phenomena inside the cell. So first we can flushing like gas by the CO2 gas and also water from the cell. So we can just flowing the CO2 here inside the cell, and also we can use the vacuum pump, and then to remove any kinds of the carbon dioxide or any kind of the gas left inside the cell. And also we can load like CO2 from here, and also the any kinds of the ionic liquids or biological buffer from the other side, and mix. So here we can increase and decrease the pressure by manual hand pump. So this actually is manual hand pump. So you can increase or compress the liquid, and also you can decrease to see the phase transition. So once you see here that we can observe like this is, it means that CO2, and CO2 is this small bubble. Jadi yang bubble kecil ini itu adalah CO2 capture, yang fraksi CO2 capture yang diinjek. Nah, mungkin ada pertanyaan dari adik-adik, bagaimana kita tahu fraksi dari CO2 di situ? Jadi di syringe pump kita bisa mengatur volume atau inject sesuai dengan volume, specific volume. Nanti kita akan hitung dulu dengan menggunakan density. Jadi density CO2 kan available di NIS ya, di data thermophysical properties itu ada available pada suhu sekian, density CO2-nya berapa. Kemudian kita bisa tahu volumenya nanti mole fraction yang kita akan inject. Misalkan mole fraction yang mau diinject 0.1. So we can calculate the total volume, how much that we should inject inside the cell. So this syringe pump, we can adjust the volume that how much we would like to inject. The same also with the liquid phase. But the liquid phase, because you have the new ionic liquids, you don't have the available data for density. So you need to measure, use the high pressure density meter. So we have another equipment to measure specifically for this. So then you can calculate the same for the total volume and inject, compress, mix, and then observe until they appear one bubble. So this is one of example. I have the previous with another compound. This is one of example. So have CO2 and the liquid, but it's homogeneous phase because high pressure. Once you decrease the pressure here, you will have vapor liquid transition. So this is your CO2. So to apply the CO2 capture, it means that you need the 1.77 megapascal to capture 0.2 mole fraction. For example, here we have bubble point CO2 with the ionic liquid. So you have 0.102 mole fraction CO2 at 45 degrees C. And then once you increase the pressure, totally homogeneous. Jadi satu fase. Di dalam sini ada CO2, ada ionic liquid. Tapi kita nggak bisa lihat CO2 itu gas apa, apakah ada gas CO2 dalam, karena nggak ada bubble kan di sini. Jadi ketika kita increase atau naikin pressure-nya, maka dia akan berubah jadi satu fase. So they will form the single phase. Then when you decrease the pressure, start, and you will form the small bubble appear on the top of the cell. So this is we record as the bubble. So bubble point, it means that you have the transition between your liquid phase and the vapor. So at this pressure, if you want to absorb CO2 0.1, use this ionic liquid, at least you need 0.51 megapascal. So around 5 bar, it's very low pressure, I think. To absorb 0.1, and then you need 5 bar, it's still low. We can say that it's low pressure, like it's not that much high. Then the others, this is one of the comparison. We have different temperatures from 303 up to 348. So we can see that here 0.1, you need 0.29 megapascal. But once you increase your CO2 mole fraction up to 0.5, you need around 7.04 megapascal. So around we can say 70 bar. Yeah, it's quite large because your CO2 is 0.5. So up to right now, if you saw that in the research data about ionic liquids, is not much ionic liquid that can absorb 0.5. So it means that once you can absorb 0.5, it's highly efficient for your system. So we can try to increase the temperature and decrease to see that how large the pressure that we need to capture the CO2. The same with this. This is I compare with different ionic liquid. I just increase the acid. I use this is propionic acid. This is butanoic acid. But I don't suggest use this one because it's not green. How to say that? It's not. I could say that the smell is not that good. This ionic liquid, the butanoic, it's very bad smell. But it's good capture. I mean, like the good capability to capture also. Only the smell is not that good. Propionic is better. Even if you take a look in this curve, we try to compare with the butanoic acid. Why I just use this is for just for the comparison, because the smell of the ionic liquid is not that good. That's why we just measure for data. So here, even if you check that the pressure from the short chain of the acid, it's better than the long chain. It means if you increase the chain of the acid, it will be getting increasing. It will be not that much efficient. So the most important is the cation in this ionic liquid. That's why we call it protic ionic liquids. For the cation phase, this is disopropyl ethyl amine. That's more important, play important in the CO2 capture. Okay, the rest I use the comparison for the CO2 in ionic liquids and also with the buffer. So we use some kinds of the buffer comparisons, and also this is kind of organic but still green. So we can see that here that the ionic liquid is actually it's much better to capture the CO2, because if you saw here the mole fraction you need 0.1, but the pressure you need only 2 bar. But if you check here the other, the concentration of the oxygen, the carbon dioxide is not that much high, right? It's like 0.01 or 0.02, but you need the pressure is quite high, 43 megapascal. So it's not that much efficient to capture the CO2. So ionic liquids is a good suggestion. So once you get this data, we need to calculate, or I could say that the prediction. So this prediction we use Aspen Plus simulation to predict, to design the process flow sheet of the CO2 capture. So this is one of the proposed, like you have absorber and also stripper. So to optimize this process or this column design, of course, once you do the experiment, you need to apply this data, how to predict the process simulation design. For example, here, to optimize the absorber, we can use this interaction. This is, we call it interaction or binary interaction. We have the Kij and Lij. I will not discuss that much about this because this is a little bit thermodynamics. So the application of this interaction, it's to design our plan. So the plan actually, when you design distillation absorber, you should have this data. So this data, it's coming from experimental data. So without experiment, we couldn't predict or design our process. This is why experiment is also one important part. Okay, so this is with the Aspen Plus. Other, we have the molecular dynamics. So molecular dynamics actually basic by the computer simulations, atoms and molecule, the same basically like interaction. So we can calculate based on the atomic level and also microscopic properties. So in this case, we not only predict the equilibrium properties, but also dynamic. So we can change the time, according to the time each of the molecular dynamic simulation. So the software that we use is a GROMAX 2020 and also topology builder for ionic liquid and some specific NPT. So here is specific condition, and we have different time, 2 nanosecond and up to 100 nanosecond. So here if we see that the ionic liquid, it consists of cation and also anion. We try to check the interaction between ionic liquid and CO2 force field. So we can see that the CO2 molecules actually, this is the CO2 and this is the ionic liquid. They are located in the hydrophobic of the ionic liquid. So they have many interaction, electrostatic van der Waals. Yeah, this is a little bit theoretical actually. So once we see that actually, like if we try to compare here that the disopropyl ethyl amine for the propionic acid and the butanoic acid, the propionic, it's getting much higher energy compared than the butanoic. So it means that they have more interaction with the CO2 compared with the other butanoic ionic liquids. So that's why this is important. If you would like to predict the types of ionic liquid, I suggest you can use the Cosmo or you can use the MD simulation. Other biological buffer, also we can use
Sebentar, sebentar Bu Dewi.
Silakan Kak Anton.
Bu Dewi, tolong dimatikan mic-nya. Ya.
Terima kasih. Mohon maaf, saya
Silakan.
belum biar lebih jernih. So biological buffer of organic substance. This is kind of the biological buffer we can use. So actually, this is, I can say, is not efficient to capture the CO2. Use this one, but some research they try to find the good way. At least can use something biologic, because why it's not efficient? Once you use biological buffer, you need to use water. So kita harus gunain air. Sementara air itu interaksinya nggak terlalu bagus dengan CO2. Contohnya, misalnya kita punya botol minuman, kita buka di atmosfer. Apakah ada gas solubility dari atmosfer ke dalam botol? Misalnya ada nggak air yang masuk ke dalam botol ini? Ada, tapi kecil sekali. Karena tekanannya 1 atm dan juga membutuhkan tekanan yang besar kalau kita deal sama air. So therefore, like biological buffer, actually, I'm not quite suggest for the CO2 capture, but I just discuss here because we also ever measure these kinds of the solvent to predict the CO2. So the important characteristic why we would like to use the biological buffer to see the interaction and also how efficient it is, because it's very seldom people discuss about this. So what's the important, like water solubility? Because of course you need to dissolve in water, and also no interference for biological process. This is the most important. Non-toxic, this is also, that's why we have the lot like chemical stability, purify buffer, and also water to stabilize. So in this case, like how their trends, actually there are many but type of the biological buffer, but ones that the mostly used is goods buffer. The name is like Goods. Goods is the founder. The founder name is Norman Goods. So long time ago, they tried to, he is actually biologist, to predict or to obtain some new biological buffer that they have the stabilize of the pH. So here we can see like around 7 or 6 to 7. So 5 to 7, it's almost pretend to natural. So the pH, it stands to the natural. And currently, like many industry, they sell about the biological buffer. So from the 2023 up to 2030, this is the predict biological buffer will be a lot in the market. And also type of the biological buffer I use in here is goods buffer. We buy the chemical, we cannot produce by ourselves because this is chemical substance, and we have the EPPS and bicene. So this is kinds of goods buffer. So why we say that goods? Because the founder, and also the pH of this is tends to stable like natural pH. So this is good high water solubility, low cell membrane permeability, consists acid base dissociation constant, and high chemical stable. So we would like to try these two chemical in the CO2 capture. So how to do? We have the isothermal VLE apparatus here. Yeah, so basically these kinds of the equipment, you can measure the same like kind of the phase to see the how goods your system. This is one another chemical that I think it's more easy to explain. Use this one. I have later about the buffer also. So for this chemical, it's binary. You can put any up to 3 component, and you can use the GC gas chromatography to divine the vapor phase and liquid phase. So the same, we have the equations in here to predict that our data, is it follow the theoretical parts or not. So how to operate this one? We can inject, sama kita masukkan mixture-nya. So inject the sample, inject the any kinds of mixtures inside the equilibrium cell. So this is equilibrium cell, and you have the thermostatic bath in here with the maintain the control or the temperature control here up to which temperature that we would like to measure, and this is the pressure, and also you have the kind of the some pump, yeah, to circulate your mixture, because this is you cannot shaking, so you need pump helps to promote the well mixing inside. Then you can inject, use the online, go to the GC to check the vapor phase and the liquid phase. Therefore, you can obtain this data. So here is a 4 CO2 capture. Others also, we have the semi-flow type. This is another type. So you will flow the CO2 here into to the pre-saturation, number 7. This is CO2, and CO2 number 8 is already consists some of your mixtures, and you will combine with the CO2. So basically the same. We will take the vapor phase and then we take the liquid phase. So you can measure by gas chromatography. Jadi gas chromatography itu adalah jenis instrumen yang kita gunakan untuk mengetahui komposisi, berapa komposisi CO2 di dalam larutan tersebut, atau berapakah jumlah komposisi si solvent yang ada di dalam mixture tersebut. Kita nggak bisa menggunakan patokan mixture di awal, karena mixture awal dengan mixture ketika kesetimbangan itu komposisinya akan berbeda, sehingga kita harus menggunakan instrumen khusus yang bisa mengukur jumlah komposisi ini. Nah, ini jenis semi flow type. Jadi alat-alat ini kita rakit secara manual. Jadi ini kita nggak beli dari company, kita beli company-nya hanya equilibrium cell-nya, selebihnya kita rakit sendiri. Nah, ini untuk validate ini, karena alatnya baru, kita bisa menggunakan sistem-sistem yang sudah publish sebelumnya. Kita bisa validasi apakah alat kita ini sudah bisa memvalidasi paper yang sudah publish gitu, sudah bisa repeat data apa belum. Kalau belum repeated data, mungkin alat kita belum bisa di-validate. Jadi kita harus validasi dulu sebelum, atau kita uji ulang dulu, uji dengan sistem yang sudah publish, kemudian baru kita bisa ukur sistem kita. Nah, ini yang CO2 tadi dengan biological buffer. Ya, nah di sini ada perbedaan konsentrasi dengan fixed mass fraction of the bicene aqueous solution with different concentration of CO2. So we varied concentration. That's why if you compare with the ionic liquids, right, this is just 0.02. It's very, very small. But the ionic liquids, you can measure up to 0.5 or 0.1. Why? Because we have aqueous. Aqueous, it's water. It means ada air di dalam sistem tersebut, sehingga itu juga bisa hindered kemampuan dari solubility chemical tersebut. Nah, di sini kita bisa lihat we have 6.27 megapascal up to 13.44 megapascal. Jadi around 134 bar. Dan dia baru bisa capture sekitar 0.04. Nah, except this one. This is one data is 3 data. It's about VLLE. So they have 3 phase. So it's not that good to capture the CO2. VLE, vapor liquid, it's better. The same. The other also, we have the bicene aqueous solution. So if you compare with the fixed concentration CO2 and different concentrations of the buffer, we can see that lower concentration buffer or increasing concentration buffer, they can obtain lower high vapor pressure. So lower high vapor pressure, lower vapor pressure, lower pressure is good or not? Maybe some of you will ask about this. Of course, we would like to capture high concentration CO2 with low pressure. Why we don't prefer to operate in the high pressure? High pressure is really costly. It's very expensive. So except in the some process like cryogenic or maybe like the kinds of catalytic that maybe they already like high pressure, it's probably no problem. But for some system that you specifically just use for CO2 capture, it's better to choose some solvent. They have lower pressure, but they can absorb high concentration of the CO2. So the same here, we need to calculate the binary interaction parameter, and you can optimize the, let's say, some absorber here. You can use the CO2, and once the CO2, this is fresh feed, fresh solvent, and then here you can use the buffer, and other the fresh feed is a CO2. So CO2 will go out, and they will go to the absorber too, because maybe some CO2 will have after the from the outlet of the absorber one, then they will go to the second one. So seldom in industry just use one column. They mostly use 2 column or even 3 column to totally purify their air or gas mixtures. It's impossible we just use once. Of course, we use 3 or 2 in sequence. Then in here we can try to recycle, yeah, even buffer solution here can recycle again to here. So that's why we need this interaction parameter. Okay, before I go to deep althetic solvent, maybe some students here, maybe do you have some question probably?
Sudah ada yang masuk pertanyaan.
Oh ya,
There is
boleh.
one question
Hmm.
from Aida, Bu Aida ya? Bu Aida
Ya, Bu Aida.
Zulaika. Miss Adila, can you explain regarding the use of solvent in CO2 capture technology? Is the use of solvents can be replaced by the use of other compounds such as catalysts? And is it more efficient in the term of process stage and yield results than the use of solvents? Thank you. Okay.
Thank you very much, Bu Aida. Nice to meet you. Yeah, so actually, like the type of solvent, we have many kinds of the CO2 capture, like deep authentic, biological buffer, ionic liquids, or physical solvent and chemical solvent, even amines. And then Bu Aida mentioned about catalytic. Yes, catalytic actually we can use. This is mostly we apply for the adsorption. The adsorption belongs to the surface. Like we have later the CO2 storage that, for example, like catalytic hydrogenation. So this is to convert the CO2 become the chemical. So we need the catalytic. So catalytic in here, we can use the metal organic framework. So later I have the chapter for the metal organic frameworks that we could use to capture the CO2. So not only always the liquid phase, for the absorber, we can use the liquid phase. But for adsorber, we can use the catalytic or we can use the metal organic frameworks. Is it answer the Bu Aida questions? Maybe further, if still have questions that I could we could discuss for further. Okay. I think Dr. Anton, I will continue first.
Yeah,
Okay,
continue
thank you.
first.
So we
Hold
have
on.
the, okay, sure. Deep authentic solvent or, pardon?
No, there is one question from
Yeah,
Pakindi.
yeah.
Okay. Pakindi?
Right now or just follow the list first?
Okay, you can wait until the end of presentation.
Okay,
Okay.
Okay. Thank you.
okay.
Thank you so much. Oh, I'm really like it. I have questions. Thank you so much, Bu Aida and Pak Kindi. And I would go to the deep authentic solvents or DES. So this is kind of the type, so we can say ionic liquid, but actually this is just preparation. So what's the authentic solvent? Actually, authentic solvent, It's like kind of the combined mixtures from the salt and metal organic. In here, I use the metal and we use the salt, kind of the organic and the metal salt. So in here, like we try to combine with the specific molar ratio and try to melt. For example, based on this curve, what the aesthetic solvent itself. If we see that this is pure compound A, this is pure compound B. So if we take a look the curve, the T to get the liquid phase in here, above this liquid, above this curve, this line, this is liquid phase. We need very high temperature to become, to let it, the compound A and compound B is become melt. So we can mix them with the specific molar ratio, and then when they mix with the specific compound, they will find eutectic points. So this eutectic point define that melting point is lower than the pure each of the substance. This is, we call it deep eutectic solvents. So deep eutectic solvent basically is more easy to prepare compared than ionic liquids, because ionic liquids we need to titration and we need to wait overnight, we need to purify, but here we just mix. And if you would like to purify because of water content, it's fine. We can use the rotary evaporator for a while and check the water content by Calvisser. So probably like it's even we don't do purification, I calculate it's around 10 ppm. It's depend on the purity of each of the substance itself. Like if you use like the chemical is already 99.8%, I think the impurity will be less, right? So in this case, the DES application, it's many. Gas capture, catalyst, yeah, like Bu Aida mentioned about catalyst for the liquids. Also, probably it's we can use deep eutectic. It's many publication appear for the deep eutectic solvent, especially for the catalyst application. Thera- therapeutic, therapeutic the application like therapy, yeah, therapeutic application, extraction, and the separation. So in this case, how to prepare. For example, here I just use common. This is hydrogen bond acceptor and hydrogen bond donor. So basically, deep eutectic solvent, they have HBD and HPA. So HBD, this is a hydrogen bond donor, and then hydrogen bond acceptor. We divide or we combine with the specific molar ratio. Let's say in here 1 divided by 4. So I use one of the choline chloride for the metal, for the salt, and also use the organic. It was the 4 times of the molar ratio. So here we can see that it's very clear. Actually, no double phase, just single mixtures. So looks like this. Actually, basically before we do like we have the choline chloride is like solid phase, and then TEG or basically ethylene glycol is like liquid phase. So if our heating is not in the eutectic point, supposed to be it's go to here, or even it's lower than this, it's not exactly at the point. So the formation, they still have the crystal inside. So this is, we call it heterogeneous phase. We have the solid and liquid, and it's from the crystal. Once it's a suitable, it's totally liquid phase. Is we can see it's like this picture. This is homogeneous phase, no solid phase. Then what's the trends? The same, we have the publication, and also currently they try to go to the market also for deep eutectic solvent, like natural deep eutectic solvent, yeah, keep increasing every year. So and we have the application like energy fuel, electrochemistry, and so on. So there are many journal and try to find the application, new application of this deep eutectic. Even currently like semiconductor or the electrochemistry, they try to use the deep eutectic solvent to even for the battery. But battery, I think no need very green. Battery, it's always they use the toxic solvent because it's more have the more it's for the ion like lithium ion, it's more better transfer compared than use the green. For the CO2, we can use the green for the capturing process. So what's the apertures? We can use like a CO2 cylinder here, and then some the valve, and we have the diffuser or gas absorption tank, and you can use the some magnetic stirrer with the hot plate, and we can measure the pressure gauge. So to measure the sample, We can use GC by online for the gas phase, and liquid phase we can take it out by manually, like by the valve. So number 6 we can have this is some pellet, yeah, and then 7 it's magnetic stirrer. So how to measure the CO2? So in here we have the CO2. It's around 0.0 something, so it's still less, yeah. For deep altetic solvent, for this it's ionic liquid. Previously it's much better to capture. In here we have the very less, like 0.08, but this is you need very low pressure. It's true, like if you take a look at this curve, maybe it's the CO2 is not that much compared than CO2 absorption in the ionic liquids, but the pressure needs, it's very not, it's not that high. I think, yeah, it's around 1,500 kilopascal. So it's quite practically in the application, it's quite good also to apply these kinds of deep altetic solvent. So actually you can increase the ethylene glycol chain, not only TEG, we can use maybe different molar ratio like 1/2 or 1/8. So it's no specifically how much the molar ratio. So we can play with this concentration. So the mechanism actually, once we have the absorption, of course we have the water content inside, because DS basically consists of the water content. So the CO2 absorb. This is liquid phase, this is CO2 in the gas phase. Once they come to the liquid phase, this is we call it absorption. And then once we release the CO2 go out, this is we call it desorption. So to regenerate this mechanism, the CO2 absorption in DS is not difficult. We just reduce the pressure, so the CO2 will be released. That's why we need to synthesize physical solvent. It's more advanced, like many advantage compared than the chemical absorption. If we calculate the design of the process, it will costly if we use the amine or some of the corrosive liquids. Cheaper in the first, expensive in the maintenance. So somehow industry, they just don't want to try new solvent because of need to build again the new system. Actually, if you calculate, is the DS or the ionic liquid is not that expensive. It's depend on the we choose the chemical. Expensive or not depends on us, because they are actually like designer. We also designer, but we design some liquids that it should be cheaper, it should be more efficient, so they can use these kinds of green solvent to replace toxic solvent. So one of the measurement in here, we try to reuse the same of the ionic liquids to capture CO2. So here, for example, like use this DS pattern. So this DS, for example, we have let's say we have the CO2 absorption around 27 in the first, but once you use the second time, use the same. So after we release the CO2, we inject the same mole fraction and try to see the capability, or try to see the CO2 concentration. So if you, as shown in the curve, is not that much different efficiency, right? It's almost practically, of course, they will reduce, because somehow once you release, it's not totally released for the CO2. So we need to purify many times. So how to purify? Yeah, we can try to decrease decrease the pressure, and also somehow for DS we can use some evaporator to totally remove the gas and also the impurities inside. So here, after 7 times, we can see that the difference is not that much, but they still can absorb around 0.1, yeah, or 0.15. So it's quite good candidates to CO2 capture. And this is, we try to compare. You have 3 different ionic liquids, for example. So in this case, we have the different water content, 5 to 25 mass%. So if you increase the water content inside the ionic liquid, so basically like what happened in the capturing process. So we can see, for example, like some of them, they will like mostly like they will decrease. but others, like let's see here, of course they will have some fluctuation, they are not that constant. So in this case we can try to divine that when we increase the water content, so they will affect the capability of the ionic liquid. So basically less it's much better. So here probably they have some specific interaction. We should go further this study to check, maybe we can use the molecular dynamics to see the energy total. So this is CO2 absorption, and also this is the last that I have, the metal organic frameworks for the liquid methods. This is only CO2 capture still. So metal organics basically is we use in the adsorption part. So we can use for catalyst, we can use for CO2 gas capture, because it's like pore, it's like solid powder. So if we saw from this figure, it's like powder, like salt, almost the same, but the pore is really small because it's nano, mostly is in the nanometer. And also here we can see that the ones of the typically metal organic frameworks in here. Why we say metal organic frameworks? Because it consists metal knot and organic ligand. So this is the red color is organic ligand, and the blue one or the purple one, this is metal knot. So basically like kerangka frameworks like kerangka. So inside the frameworks we can fill with something, probably like the CO2 gas or CO2 hydrate. So it's possible they will fill inside this pore, and this pore is very small. That's why the areas or the surface area, it's really huge for the one of the metal organic frameworks. So one of the most is the ZIF or zeolitic imidazolium frameworks, code 8, because they have many types like 8, 67, and so on. So we choose in here 8 because it's practically is good for the CO2 capture. So it looks like this for the synthesized ZIF8. Then how the process? In this case, I don't use just ZIF8. I will encapsulate with the ionic liquids, that the good one that we measured previously. So we encapsulate with the ionic liquids to increase the CO2 capability. Actually, it's not all increase the solubility, because some of the high energy, like high pressure, the high pressure part, the pristine, the pure ZIF8, it's still better than the when we combine. But some like low pressure, it's better for the encapsulate ionic liquid with the ZIF8. So this how the way we use the zinc nitrate hexahydrate with the 2-methyl imidazolium. This is organic ligand and metal knot basically. So we synthesize first. So we don't use the any heat to synthesize. We just use room temperature, so we can save the energy like around 12 hours. Actually, like if we ever try use like 4 hours or 8 hours, but the synthesize optimum condition, the yield is not that much. So that's why we leave it for 12 hours longer. It's more ZIF8 that we can obtain. So once it's totally mixed, we do the centrifuge, use the 12,000 RPM, and we wash with the water, just wash with water 5 times. And after this, we use the freeze drying. Why we don't use the oven? Oven is not good for metal organic frameworks because it can reduce the capability of the absorption process. That's why we use the freeze drying. It's much recommend. It's okay use the oven, but the capability absorption they will affect. So that's some journal they mention oven. That's the maybe they can they at that time like they would like to compare, or maybe they try some method if high heat, like how the capability. But we tried previously to check freeze drying is most best suggestion to remove the water content from the ZIF. Why we use this one? We want to remove the water. Of course, from the centrifuge, you cannot totally remove the water. So, untuk menghilangkan airnya, kita harus menggunakan freeze drying. Jadi nanti kita akan obtain benar-benar material yang dry, dari Ziv 8 itu tadi. Jadi Ziv 8-nya itu benar-benar pure dry, nggak ada water sama sekali. Nah, kenapa kita nggak pengen water? Karena akan mengurangi daya absorpsi dari CO2 tersebut. Jadi setelah ini bagaimana kita bisa encapsulate dengan ionic liquid? So we use the pristine Ziv 8 and we combine with the ethanol and the ionic liquids. We need the help from the ethanol a little, not that much. So what's the function ethanol here? To reduce the viscosity of the ionic liquids, because this ionic liquid a little bit viscose. So if you use viscose and then this is powder, your encapsulation process is not that much good. Then the same process, mix, and then we remove by the freeze drying. And the characterization, use the FTIR, XRD, TM. So FTIR, we use the Fourier's transform for the infrared. Yeah. So in here, like we have the XRD also, X-ray diffraction, and then we have the TM for the we would like to calculate the transmission electron microscopy to check the surface morphology. For the XRD, we can check the crystallization. For the FTIR, we can check the compound that it's probably like unknown, because here we would like to confirm. Actually, this is just based on the confirmation. Is it the ionic liquids and the Ziv 8, it's totally have inside this material or not, or they are not form another chemical. So basically how we did, like this is one of the spectra FTIR and the XRD to compare with the different mass fraction of the ionic liquid. Basically they are not that much different with the Ziv 8. It's almost the same, like the stretching bond, yeah, like for example around 3,465. Yeah, this all is have a peak. So it's just to confirm that when you combine or composite, this is, we call it composite, and then with the Ziv 8 itself, they no change. If they have a change, it means like maybe it's not that chemical we want, but they change to another form. The same is the XRD pattern, like 011 up to 222 is almost the same here. So nothing that much different with the pristine Ziv 8. So before and then after we encapsulate, so basically the FTIR and XRD is confirmed with the pristine Ziv 8. And also we do the TM for the transmission electron microscopy, or the TM itself, to check the morphology of the our material. So in here, like before encapsulate, let's say this is pristine pure Ziv 8, it looks like benzene, yeah. The structure is like, yeah, like benzene. So here, once we encapsulate, so we can see like this is almost like dark color and then the gray color. So it means that our ionic liquid, it succeeds to encapsulate inside our pristine Ziv 8. So this is just confirmation what's the form and then how the surface layer of our compound, like how the, let's say that our material, is it becomes totally successful the composite, composite or not. If we compare here, like it's successful, the ionic liquid, it's totally go inside the pore of the metal organic framework. So we can see from the proof. So how the design apparatus, so we design CO2 high pressure syringe pump. So here we have the fixed bed absorber. We just inject or put inside and control the temperature. And also we have oxygen trap to remove the moisture from inside. So once the pressure in and out, so in here we have PI or pressure indicator. Once you have inlet and outlet is equal, so it means already reach equilibrium, and we can take some sample to measure the flow rate and also to check the composition of the CO2 that inside the or absorbed in the system. So if the pressure is still not the same, it means still not reach the equilibrium. So we're going to try like from the low pressure up to high pressure. So the curve will be like this. So we have the open solid circle, open circle, and then also the open diamond here. The open circles is belongs to the ZIF8, and also the open diamond, it's belong to the ZIF8 encapsulate with the ionic liquids. So if you see here that low vapor pressure, they have the pristine or the composite, it's better than the pristine, like no ionic liquid. So you see that this is mass of CO2, so this is practically much higher. For example, the same pressure, the open diamond, it's getting more CO2 compared than the pristine one. So the composite, it's better for the pressure 0 up to around 20 bar. This is good for flue gas application. But for the high pressure, 20 bar up to 56 or 55 bar, the pristine ZIF8, it's much better. So that's why they have some cross section or cross point in here. Cross point over like around 16, they have cross point. So what's the solid circle and then solid diamond here? It's simulation. We use RASPA software. So we got to have the SIF file or SIF structure first from the single crystal XRD. So if we don't have single crystal XRD, we can use Material Studio to make the, let's say, to predict the molecule first, how the interaction and molecule charge. So we have SIF file, because SIF file actually have data bank, but for the ionic liquids or new MOF, we don't have. So the one possibility, there are two possibility. We do the experiment single crystal XRD to divine the SIF file, and then SIF file can use for the RASPA simulation, or we need to obtain or draw by ourselves. So we need to divine the charge of the CO2 inside the molecule or everything, and we can divine. But still, the simulation, especially high pressure and then low pressure here, they cannot totally predict. The reason why, because this material is flexible, and the RASPA, it's a static simulation. So the static and dynamic, of course, they cannot totally predict very well. So like the material, it's so cool. It's like they can moving. Even the high pressure, they are totally flexible. So even in the pore. So that's why here, why the experiment and the simulation, they cannot totally, the simulation cannot totally predict the real experiment, because this is static. The same like this one is a static. If some of you ask, like, is it possible we use dynamic? Yes, but is quite challenging to do, because it's like a different time and different pressure. So we need more time to do this one, and more variable. So we need to adjust. Still possible to use the dynamic simulation. So the same here also. We can see that this is more, even high temperature also cannot predict totally the experimental value. Okay, that's all for the CO2 capture. I will go right now to CO2 storage and CO2 utilization. So actually we discussed previously, like we have CO2 sources and we capture. So we capture the process. We can use two parts, like CO2 utilization and the CO2 storage. What is this? Carbon dioxide utilization is like gimana cara kita mengconvert atau menggunakan CO2 ini konversi dengan menjadikan renewable energy lain atau jadi bahan chemical lain. Nah, itu CO2 utilization, kayak lebih ke penggunaannya. Tapi kalau storage itu lebih ke arah penyimpanan dalam waktu yang lama. Jadi misalkan kita injekkan lagi ke well yang seperti tadi, itu prinsipnya storage. Kita nggak ngambil lagi, tidak mengambil CO2 lagi atau menggunakan CO2 lagi untuk kebutuhan lainnya. Nah, di sini ada dua part. Jadi untuk CO2 storage sendiri biasanya penggunaannya for CO2 hydrates or CH4 hydrates. Currently it's hot topics, enhance oil recovery. So we can use CO2 to blue the oil. Jadi kalau di dalam well itu kan ada ada oil. Nah, untuk untuk menarik oil itu di dalam well, kita bisa meminta bantuan dari gas CO2 atau saya pernah lihat di Riau kita biasanya menggunakan steam. Kalau dulu menggunakan steam flooding karena memang jenis karakter oil di Riau itu terlalu kental, heavy oil. Nah, heavy oil bukan light, jadi kita harus menggunakan steam yang benar-benar steam flooding yang dipanaskan kemudian diinjekkan ke dalam well untuk menarik si minyak di dalam bumi ya. Nah, sekarang diganti, jadi tidak menggunakan steam flooding, tapi mungkin ada beberapa, sekarang mungkin Pertamina masih menggunakan, saya belum tahu update-nya yang dari Riau sekarang penggunaannya bagaimana. But some researcher they try to use the CO2 to replace to blow the oil and also can get some CH4 from the under the sea or under the on shore or offshore. So in this case, like they have they can also use or apply the CO2 storage for the enhanced oil recovery, and also that's for the well technology. So well in here maksudnya tuh proses bor atau well teknologi welding teknologi well ya, teknologi well ketika kita melakukan pengoboran minyak itu bisa menggunakan salah satunya CO2 untuk membantu minyak tersebut naik ke dalam pump oil pump. Jadi kalau pernah mungkin adik-adik pernah lihat pompa yang seperti angguk-angguk itu, dia itu sebenarnya pompa oil kan, dia narik oil dari dalam bumi. Nah, di situ kita bisa menggunakan CO2 juga, dan and then CO2 utilization we can use as reaction medium like supercritical carbon dioxide. This is also very hot topic and famous. We can use carbon dioxide, but in the critical level, above the critical level, for the extraction, for the adsorption, particle formation, so many application. For polymer, we can use for the supercritical carbon dioxide. Calcium carbonate also, we can form CaCO3 from the CO2. Jadi penggunaannya bisa untuk keramik, bisa untuk paint, cat dinding. Jadi kan semuanya perlu CaCO3. And then also we can use for syngas like to form hydrocarbons, alcohol, or any chemicals that we need, but still need high energy. Hydrocarbons like CH4 and the higher hydrocarbons, and polymerization like polycarbonates, plastik ya, untuk electronic device. So, jadi banyak penggunaan CO2 utilization. Nah, di sini saya mulai dengan CO2 storage. So this is first is CO2 hydrates, and then we use also CH4 actually. So we have the high pressure cell here, and then we inject the CO2 inside the cell, so we can see that this is a kind of the fuel cell. Jadi kita bisa lihat ada apa sih yang terjadi di dalam gitu. Ketika kita inject CH4 mix dengan CO2, bagaimana dia CO2 tersebut bisa replace CH4. Nah, di situ kita perlu melihat prosesnya. Jadi di dalam in the CO2 hydrate we have the step like before depressurization, it means that totally form the methane hydrate or CO2 hydrate here. And then the first stage, when they are decomposed, they will start to have the liquid phase. And the end of the hydrate is totally like fully liquid phase. And this is we can see that actually like this process is by the cycling. So once they have the CO2 or the CH4, when they are replacement, in here, like originally CH4 under the sea is of course is like ice. So if we see that the under the sea, or let's say that under the earth, the pressure is very high. It's not low pressure, like very high. And then the temperature is very cold in there. It's very extreme, the temperature under the sea. So that's why the CH4, they will form as the solid phase. Then once you inject the CO2 inside, they will try to change or release the CH4 with the CO2. So CO2 inside, they will become the solid phase. So here they start to melting, and then they release the CH4. And then once the CO2 form, they will come back to the first stage. So once we take something from the earth, we should replace with this with something to the earth. We cannot we cannot let our like, let's say, when you take the CH4 and then you just keep the empty space there, they will let's say that lempengan bumi itu bakal crack karena kita perlu menggantikan sesuatu yang kita ambil. So we should replace like some things like CH4. If you take the CH4, you need to inject back CO2, or you need to use some other gas substance that you should replace this. So otherwise, it will be dangerous. Maybe have the earthquake or something like blow up, not like we can say that blow down. Yeah? That's one in the gas phase. We can use like lumpur lapindo. That's one of the case also happens. So that is the high pressure and then go up. So that's why we need to very careful. This technology is still new and it still belongs to the research, which condition is good, which kind of even we should have the chemical, not only pure CO2 hydrate, but also we need to find some chemical that can help the CO2 when go to inject the well. They should practically form the CO2 solid should be fast and its hold should be the CO2 in the long term. If you just use the pure, I don't think it will work because you still need some we say that hydrate promoter to some chemical that increase the hydrate formation faster, and we also need CH4 inhibitor. So to let this chemical can let the CH4 easy to release to the pipe, yeah, because it's not easy to from the solid and then you got to change it to the gas phase. So that's the challenging. So currently I heard that Pertamina try to develop this technology, and this is one of the possibility like CO2 injection here, and this is you have the impermeable CO2 hydrate cap, and this is natural gas hydrate zone. So once you take here, you should replace something to your gas. Of course, we cannot just let it empty. And the other the same. This is practically like if you have coal fire or any kind petrochemical industry, and they will inject something for the hydrate zone and take it the CH4 rich gas and the production wells. So they in the future like we can storage the gas inside the ice. So hydrate is ice basically. So hydrate itself, it's from water in the like this one it's water plus gas and become like ice. The foam actually I ever burn on my hand. I don't feel that this is hot actually. It's like ice melting. So you can storage even the gas by the ice, but you need to be careful because uh, this one it's CH4 is the flammable gas. That's why in the future they just use for the gas production. It's not for the storage. It's not for the replacement the cylinder. Yeah, still in cylinder, but they just use in the well. So that's why this is belongs to the pre-combustion. So pre-combustion, the CO2 amount it should be large. We cannot use 5 to 15. It's too expensive for technology. So for this type, you should use more than 80% of the CO2. It's better. So like this for the CO2 storage, and we have CO2 utilization. One we can use for the conversion to polymer. Like in here we have CO2 propylene oxide, and we have the polymer like a polycarbonate, cyclic carbonate. This is side product, and this is the polycarbonate. It's the main product. So we need to use catalyst. Of course, we cannot use or promote this reaction without catalyst. So this conversion, it's possible, but still quite expensive. The application is like nanoparticle for drug delivery, hydrogel, many application for this polycarbonate. We can use in the like 3D printing also for the scaffolds for the inside our body, like replacement also it's possible. and also scaffolds, yeah, like some polymer scaffolds. This is we use this polycarbonate once of utilization, and also the other we can use the hydrogenation of the CO2. This is could be most promoting energy and also fruitful for the minimizing emission of CO2. So we can use basically CO2. They can produce by two ways, indirect and then direct. So it's depend on the type of the chemical. Later we need to use energy JIPS to calculate, and we have we can say that when you use the hydrogenation of CO2 to form another renewable energy like lower olefins, liquefied petroleum gas, gasoline, aromatic, this all we can produce from the CO2. So this is we can call that carbon natural fuel because the CO2 is trapped from the air, so we use to produce the fuel. And when you re-emit again, you will not increase the CO2 level because like you just use like recycle the CO2. That's why currently they try to approach this way to convert, and this is highly technology to produce like methanol and also to produce such kind of the olefins, liquefied petroleum gas, gasoline, aromatic. This is still on the research way, like but they try to apply in industry to replace the chemical organic and try to use some of the possible replacement fossil replacement, use the CO2 and also need hydrogen because C and H we can form the hydrocarbon, olefin or gasoline. So in this case, we need to know about the Gibbs free energy formations. Once we have the negative energy Gibbs, therefore our reaction it's it's a spontaneous. But once we have the Gibbs free energy is like positive, it means non-spontan. It means once you have the delta G, its negative side, yeah, they can have the reaction. It's directly promote. Even you don't need to inject or add some more energy. So that's why here we have the some energy level that probably we can form from CO2 and the hydrogen, like to form the ammonia, methane, the ethane, and so on, like CH. Mostly like C, yeah. Ammonia, I don't think it's really hard. You need to nitrogen. You cannot just use, you don't use the CO2, but for CO2, we can focus on the methanol like this, the probability like C and H, ethane like CH, and olefins, liquefied petroleum. So this is possible. So currently, like they try to form the methanol also, and try to build plant in Taiwan. They try to build the plant to produce the methanol from the CO2, and still in going on for this. And then yeah, so before we produce the methanol is maybe by the or ethanol by the food waste or food energy, like food material, but we don't want because the food is for consumption. That's why right now they try to approach the how to use the CO2 in the capture process to form the any kinds of the fuel or any kinds of the chemical that we can sell. And then this is actually it's carbon neutral because the pathway, like we capture from the air or we capture from the process, we don't release to the atmosphere, but we produce something for the some chemical that we can use to produce another renewable energy. So yeah, so in this case, like another, we have also carbon dioxide in the carbonate. So this is like we can produce for the ceramics, we can use for the ceramics, or we can use for the paint or any kinds of coatings. This is possible. So here, for example, like some solution, it's very clear. But once we add the CaCl2 and they start to form the carbonates, actually this experiment is not difficult. So we have the CO2 cylinder, you can use saturated DI water, and you have the some specific absorption, use some solution, and the CO2 excess they will eject in here, or you can check the concentration of the CO2 here, and later you once it's already reached to the saturation, we can try to use the CaCl2 and they will form CaCO3. So from the high pressure, of course, the CO2 it's or solid carbonate is higher because the CO2 capture is higher also compared than atmospheric. This apparatus we just run in the atmospheric condition. But for the high pressure, we can use the previous equipment like phase equilibrium analyzer. That's up to high vapor pressure. So we can take the sample out and try to add the sodium hydroxide and the calcium chloride and to see that the foam, how much they can form the CaCO3. So this comparison that prove that high pressure, of course, is can be like one of the highly possibility to capture the CO2. Actually, like basically CO2, we never capture at the low pressure. We always do in the high pressure because like for example in the fuel gas like the flue gas actually basically like 10 to 20 bar, so it's high pressure, it's not low pressure. So for the CO2 capture also I think the same, so we use high pressure mostly. So some paper they measure 1 atm, but I think in the application it's not uh, possible to do because in the industry mostly they use high pressure for like 10 to 15, but to form like CaCO3 like this we don't need high pressure. This one we can use like low pressure to form the CaCO3. So others like CO2 supercritical technology, this is we use for extraction. So from the CO2 that we capture we can reuse for the CO2 utilization. This is belongs to the pre-combustion. It should be large amount of the CO2. Once actually this is interesting, we use the CO2 supercritical CO2 to separate the monomethyl adipate and dimethyl adipate. So this adipic acid actually is ester, and its many application you can use as intermediate or as the raw chemicals. So actually this is from the caprolactam waste. So we can use the reaction adipic acid plus methanol and we can produce the MMA, monomethyl adipate and dimethyl adipate, and they will produce some water. So how to purify this chemical, like how to catch this chemical? So we need to extract, of course, like to get the dimethyl adipate and monomethyl adipate. One way that the most important, we can use the CO2, so we can produce some curve. Yeah. So for extraction, we will operate on this region. So this is extraction. For the absorption, we can operate below critical points. The same like this, below critical point. So why in the extraction is in the dew point? Because it's large amount of the CO2, only small amount of the solute. This is of course is a solute is very small amount compared than the CO2. So we will use this operating condition. For example, I would like to capture 0. I would like to extract 5% or I would like to extract 2% of the chemical from the by the CO2 98%. So at the some specific temperature. So that's why here we can use like, oh, the pressure it's around 10 bar that I need. So I can extract around 5%. So basically company, they need to know the operating condition because they will not do like trial and error in the large scale. They always give to the school to trial and error to measure this condition, which one is good for their system, and then later they can try in the upscale. So this one for the DMA and the MMA, that's one it's both we can use for the CO2 to do the extraction. And of course, that's most important is about the phase. Anything about CO2 capture or about the CO2 storage, we cannot neglect that the theoreticals or the experimental we really need. This is versus of engineering applications. For example, like solubility, we can use absorber like previously for CO2 capture. We need to know the VLE because the solvent is liquid phase and then the CO2 is a gas phase. We need to have this data like how the optimum condition. The same like the for the investigate potential physical solvent, we can do like in the post-combustion CO2 capture, like optimizing design and also evaluation. And the CO2 utilization, we can use many supercritical. I just mentioned one of this. Actually, we can use for dyeing also. Dyeing, it means like kita mau ngasih warna ke fiber. For example, kalau dulu ketika kita mau warnain pakaian kita selalu pakai air medianya, terus ditambah dye. Nah itu kan nggak green, artinya kita perlu jumlah air yang sangat banyak. Kemudian kita mau kemana kan limbah ini. Nah sekarang metodenya itu kita bisa menggunakan supercritical fluid untuk mewarnai pakaian fiber. Untuk mewarnai fiber itu memungkinkan dengan menggunakan supercritical CO2 atau N2. Sampai saat ini masih menggunakan CO2 karena CO2 itu harganya lebih terjangkau dan memang critical point-nya itu tidak terlalu tinggi, jadi sekitar 304 Kelvin dan 73,8 bar saja sudah mencapai titik critical point-nya. Jadi kita bisa operasikan 100 bar itu sudah mencapai supercritical dyeing. Jadi sekarang udah mulai dijual pakaian-pakaian yang menggunakan supercritical, dan juga ada supercritical micronization. So this is for micronization for the drugs. So like some drugs, they are very hydrophobic. It's not easy to dissolve in our body. So we need to micronize. So cut into the small pieces, and therefore this drug can consume very well in our body. Like let's say that we can increase their efficiency by the micronization or by the cutting. We can enlarge their surface area by the micronization process. So this is, we can use supercritical CO2 also. So many applications, and the typically important is we need to check the phase. Of course, it should be like totally equilibrium, like the time invariant, uniform, and all flows, it should be zero. This is theoretically the net of the red chemical reaction should be equal to be zero. And many like thermophysical properties that we can measure, not only for CO2 capture, but many wide of the application like VLE, LLE. So this is kind of the sharing, like we have density, viscosity, and the important, it should be reproduced. So once we find the data, reproduce is more important. That's why we need uncertainty. Every measurement, CO2 capture application or extraction, separation, we should have uncertainty, and it should be can reproduce by another researcher. It's not only us, we can measure this. But this is, I tried in the metal organic frameworks, is difficult. Because any kinds relate about material is difficult to reproduce, to be honest. It's not like the equilibrium or the phase, but also for the material, it's like making the cake. Like kalau kita buat kue, misalnya chef yang udah biasa, kita dikasih bahan sama chefnya. Chefnya udah biasa bikin, yang kita baru belajar. Tentu yang udah pernah bikin, pasti hasilnya jauh lebih bagus dibandingkan yang baru bikin, meskipun resepnya sama. Jadi itu juga external factor yang somehow difficult to reproduce for the materials like metal organic frameworks. Somehow I try, like when I go to the paper, I try to reproduce the way they did. I cannot even reproduce the results, and it's normal because they have the external factor that probably affect like the way how we make the environment, and somehow like we got to go to the science deeply. We should go to the mechanism how they can produce the fixed material so we can reproduce their results. So this is like what we learned from the metal organic frameworks. And also data validation, this actually some simple equation we use, actually we don't derive, so we just use the Aspen plus. In there we can have many kinds of the method. So this is one of the basically that we show before binary interaction parameters. It's coming from this equation. Actually, I just want to show about this. And also The conclusions, yeah, so we discuss about the calibration for the measurable variable, so for the post-combustion, pre-combustion, and data validation, data scattering, like with the sum, uncertainty, also the application of carbon dioxide storage and utilization, and the rest for the students. Once you do the experiment, you need number 5. This is the most important. Be patient. Sometimes the result you cannot get the good result. It's normal in research. That's why the name it's re and search. So keep searching. We cannot get one time we try and then we get the good result. So somehow we need to be patient. Kita harus sabar. Ketika kita ngukur, once you measure that, oh, I didn't get the good result, it's fine. You can try again until you got the best way how to get the good result. So in Taiwan, they use this one actually because this is their trust. Yeah, so they use this one. They hope that their apparatus is not broken. This is the students. The students in Taiwan, they install this in the equipment. Yeah, so it's the culture. So I would like to say thank you to my member of my lab. It's always my students, and currently they still do the measure some experiments in the 404 National Taipei University of Technology. And also I would like to say to my professor here, Professor Lim Mingjer, and I learned many things from him. So this is once I still doing PhD in his lab, because his support that I can do until this step. And also I would like to thanks to the Ministry of Science and Technology for the research funds. So thank you very much. Also, I would like to thank you to the Universitas Ibnu Khaldun that giving me opportunity to share the CO2 capture and the storage also. Hopefully it's something useful we can learn together. So if you have question, I'm really open. So I will return to Dr. Anton. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Dr. Ardila. This is a very interesting topic. Keren banget, keren banget ya. Jadi sampai saya lupa untuk jaga waktu. Oke, 5 menit lagi, 5 more minutes until we get to 4 p.m. Taiwan time. So I just give one chance to Dr. Al-Kindi to have a question. Please.
Thank you very much, Dr. Anton. My name is Kindi. I'm from Technic. I have 3 questions. The first question is, my doctoral topics is about adsorption with pressure swing adsorption technology in biogas. So I spread carbon dioxide from biogas to take the methane. So the methane can use for energy uses. My question is, what first, the gas that used was monogas that I have seen, or just CO2, or just carbon dioxide gas. So in reality, in atmosphere, the gas is vary. So it will impact to kinetic and equilibrium study, and will impact to breakthrough curve. So what next to study about the variety of the gas in atmosphere? The second question is about the fresh fuel gas. It was usually have high temperature, so the temperature make bad effect to capture of gas. How can we deal with this condition? If we modification of adsorbent or absorbent, or we adjust that high temperature gas to cool first. Nah, itu. And the second and the third question is maybe is progressive question. I have interest to study my to to continue the study to postdoctoral, or it just if the in the what campus is in your campus have the opportunity to continue the postdoctoral about the carbon dioxide capture. Thank you. That's it. That's all, Mr. Anton.
Thank you very much for the question. There's 3 questions. For the first is the absorption on the biogas separation from CO2 and to take the methane gas. And then also the second one is the temperature high variability, how to deal with it. And then the third one is there any position for postdoctoral, because third Kindi is dealing with the CO2 separation, something like that. Okay.
Thank you very much, Dr. Anton and Dr. Kindi, for actually it's a really nice questions. Yeah. So it's according to the Dr. Kindi questions, like it's more tends to the application, I guess. So the first question is why I use the CO2 only? In the research way, actually, we try to combine also with the mixtures. So in here, I'm trying to combine like CO2 and CH4. And also we have CO2 and nitrogen. Like in the air or in the reality, actually the mixtures gas, it's a varies. Why we only use the CO2 and the nitrogen or CO2 and CH4 in here? Because some applications that they try to approach, it's the mainly gas is consists of the CO2 and the CH4. So practically, like when we buy the chemical, the gas, so we ask or request the company to give at the some specific fraction. So it's possible actually in the experiment also, we try to do the several gas mixtures. So it's depend on the company request. So somehow the company just requests CO2 and CH4 because it's mainly like their consist gas is in the field is only CH4 80% and maybe the CO2 is 20% or probably like 19.5% and nitrogen have a little, but it's not that much effect if we have the small compositions of the another gas in the mixtures. So we can do like several concentration. It's depend on the request, but mostly in the monoatomic we did because it's more easy for the experiment. If supposed to be, we would like to conduct pre-combustion. Let's say that in the pre-combustion, the concentration of the gas is highly than 80%. So we can use the almost pure CO2. Even they will evac actually with the kinetic, but in the some process, for example, the exhaust gas, or for the process like some exhaust, not the exhaust like 20% around, let's say from the pre-combustion, like capturing from the flue gas, the concentration, let's say 85. So we still can do separation first and then try to capture the just CO2 to catch. Somehow the company will not use like the mixture gas, but they just try to separate first. Because nitrogen they can use for the another process, and the CO2 that they unwanted gas, they can reuse to use for the pre-combustion like CO2 hydrate or use the supercritical fluids. So in here, I just use the monoatomic and also like binary mixture first to study from the simplified conditions as the company requests. And the second, because we would like to design for CO2 capture. That's why we use only the monoatomic, because other gas is not that much effect actually. And the second questions regarding about the kinetic, yes, Prof, about the temperature. That's interesting question. Which one I go first? If we have the high temperature, is it I should choose the ionic liquid or some liquids that can hold the high temperature, or I should cool first? This is actually, it's depend on the process. So first, we can do both. But for the cheaper, I suggest we should cooling first. This is the cheaper process. We can cooling the process first. We can reuse, do the heat integration. For example, some in the distillation or the external cooler that for the process, let's say liquefied natural gas, we have some excess cool, we can cooling down by the heat integration first, then we can use some specific liquid to capture CO2. Because once we do like the high temperature, let's say 400 or 300, our liquids like deep authentic or ionic liquids is cannot hold at the for the high temperature. They will degradable. Not only that, but also some organic solvent for the high temperature, probably they will have degradation process. So it's not good for the capturing. It's not original chemical again. So, but still, if the temperature is still within the range of the our liquids, we still can use directly. So it's depend on the temperature, how high our operating temperature. That's why when we synthesize also, we try to check the TGA, thermogravimetric analysis, to check that when exactly this liquid degradable. So let's say 200 degrees C. Mostly it's always 200 degrees C, mostly green solvent, or like let's say ethylene glycol, even 150 some. They already degradable. So we can try to cooling down first, and then we capture the process. That is my suggestion, Dr. Kindi. And the third, this is interesting question, the most actually. Postdoc position actually in Taiwan, there are many. So actually in the Ministry of Science Technology for postdoctoral position, it's open, Dr. Kindi. But in my lab, since I'm still assistant professor, I didn't allow to have a postdoc. So I should be promoted first. So I should go to the promotion, and then I could request for the postdoctoral. So postdoctoral, it should be on only professor can accept the postdoctoral positions. So in Taiwan, it should be professor only. So a professor or distinguished professor. But Dr. Kindi can take a look in the website. They have ministry. Maybe we still have time or not, Dr. Anton? I can.
Uh, we can do it later after
that's
this,
yeah.
yeah, because the
That's
time is up.
yeah. Okay. So
Okay, thank you.
that is yeah. That is many open. Only the topics probably they have different topics, Dr. Kindi. But still, we can do collaboration. Research international collaboration is possible for us. I hope the professor in the University Ibnu Khaldun, we can have keep in touch on the research in the future. Okay,
Yes,
I hope answer
insyaallah.
the question, Dr. Kindi.
Oke, terima kasih. Nanti
Okay, thank you.
keep in touch after this this meeting because there's interesting opportunity to do collaboration. So ini mungkin hanya apa namanya yang bisa kami lakukan sebagai tanda terima kasih yang sebesar-besarnya kepada Dr. Ardila yang telah menyempatkan waktunya, energinya untuk memberikan kami ilmu yang sangat bermanfaat dan sangat eye opening. Mudah-mudahan membangkitkan kita untuk melanjutkan mencari ilmu research baik buat dosen bahkan untuk mahasiswa untuk melanjutkan S2, S3 mungkin di Taiwan nanti gitu ya. Insyaallah. So this is I would like to give you the certificate from us.
Thank you
So
very much.
yeah, this is the certificate, and I will give to you directly later. And then after this, please open your camera. Open your camera because we need to take a photo together. Will be led by Asep. Please, Asep. Asep, mana Asep? Pak Asep. Asep tolong pimpin fotonya. Aba-aba, kasih aba-aba. Harus gaya kayak apa? Okay, wait a minute. Sebentar.
Halo Pak.
Ya, silakan.
Ya, kita hitung ya. 1, 2, 3. Oke, sekali lagi. Dibuka kameranya ya. 1, 2. Baik Pak, sudah.
Oke, sudah. Terima kasih semuanya. Thank you very much for your attention, and then sekali lagi terima kasih banyak jazakillah khairan kepada Dr. Ardila yang telah memberikan kita ilmu. Oke, sampai bertemu selanjutnya di series yang kedua, insya Allah akan kami umumkan melalui grup. Oke, terima kasih. Kita tutup dengan doa kafaratul majlis. Subhanaka Allahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih.
Thank you Miss Anton. Mr. Anton.
Yo. Terima kasih.